Hi guys, so this next unit is all about solutions and we're going to review the different types of matter so that you understand where solutions fit in. But I want you to take a minute and look at this little cartoon. And by the end of this video, you should be able to explain why this cartoon is hilarious. So we'll come back to that in a second. All right, so matter. If you remember from the beginning of the year, matter can be broken down into two smaller categories. Whoa, my hand's a little shaky. We have pure substances and we have mixtures. Okay, and from there we can go even more specific. If matter is considered a pure substance, it could either be an element or a compound. And in my mixture category, there are more specifically two types of mixtures. We have homogeneous mixtures and we have heterogeneous mixtures. Okay, now homogeneous mixtures are also known as solutions. So it's in this part of my matter classification diagram that we're going to be spending the next couple weeks. How is a mixture different from a compound? You have multiple substances, but they're blended together physically instead of chemically. They're not bonded together, they're just physically in the same container. And what makes homogeneous different from hetero is that my particles are spread evenly. So when you have a homogeneous mixture, it's hard to tell from the outside that it's a homogeneous mixture because it doesn't look like it's made up of multiple things. Everything's blended together evenly. It looks like one color. Where in a heterogeneous mixture, that would be like sand and water versus iced tea. Sand and water, you can tell that there's two different things in the container. They're spread unevenly, the particles. Okay, so that's just one little thing to help us review to see where we are. Okay, so as far as vocabulary goes, a solution is a whole mixture. So when we say the word solution, we're talking about the two things that make it up. So if I talk about iced tea again, I would be talking about both the iced tea powder and the water. They both make up the solution. Each thing in the solution has its own separate name. The solute is the stuff that's dissolved, and the solvent is the liquid that's doing the dissolving. So in iced tea, the solute would be the iced tea powder, and the solvent would be water, right? Both of those things make up my whole solution. In chemistry, we're going to see examples written like this. And if you remember from, again, in the beginning of the year, we used that symbol AQ to say if something is aqueous or dissolved in water. So in this example, I know that it's a mixture because I have NaCl and I have water. I have two things mixed together. Which of these things would be the solute and which of these things would be the solvent? All right, so hopefully you put down that NaCl is the solute and water is the solvent. So these are my dissolved NaCl particles here, and this is my water. And together they make up a solution. Okay? All right, let's talk about how dissolving occurs. Okay, so we're using this example of NaCl, which is table salt, dissolving in water. And what happens is the intermolecular forces that are present within the solute and the solvent have to almost rearrange themselves. So the first thing that happens when you drop NaCl into water is the NaCl, we're going to use a new word today, dissociates. And that means breaks apart into Na and Cl ions. Okay. Now, as the Na and Cl break apart, they start kind of like going in between the water molecules. So the water molecules were originally attracted to each other through the intermolecular force hydrogen bonding, but as the NaCl kind of squeezes in between them, the hydrogen bonds that were between the water molecules start to break. And now we have these ions that are squeezed in between these polar molecules, these water molecules, and now new intermolecular forces form. So I want you guys to think back to our bonding unit. What's the type of intermolecular force where we have ions being attracted to polar molecules? Ion dipole forces form. Okay. So I'm going to show you guys a cool simulation of this actually happening tomorrow. But this is basically what happens anytime you dissolve something into water. Okay. This is kind of like a step by step. So A is how the salt crystal would look at first. B shows it starting to separate. And then C shows the salt fully dissolved in the water. And then this is kind of like a zoom in of what's going on in C. So if you guys remember that water is a polar molecule, if I draw a water molecule and I look up the electronegativities of hydrogen and oxygen, oxygen has a stronger electronegativity, which means that it pulls on electrons a little bit harder, meaning it has a partially negative charge, making my hydrogens have partially positive charges. Okay, so guys, if you look at this Na plus ion, that's the purple ion in there, what side of the water molecule do you notice is facing the positive sodium ion? The negative oxygen. And if you look at the Cl minus ions, again, it's surrounded by water molecules, but what side of the water molecule is facing the chlorine ion that's negative? The hydrogen side, because it's positive. Okay, so this is how the dissociation happens and why salt is soluble in water. So this is the positive is going to always attract the oxygen, and the negative ion is always going to attract the hydrogen end of the water. And the salt particles will be able to be pulled apart. Okay. We also have energy changes associated when we make solutions. And sometimes you can actually feel those energy changes from the outside. When you dissolve something in water, the water might get warmer or colder depending on what's going on. So if you think about barf, which again we talked about in the bonding unit, to break a bond, you need to absorb energy, and to form a bond, you need to release energy, right? So when you make a solution, the first thing that has to happen is your solute and your solvent particles have to separate from each other. So if we're breaking a bond or breaking an intermolecular force, energy needs to be absorbed. So the first thing that happens is we absorb a little energy. Then when our new intermolecular forces form, we release energy. Now, deciding if the whole process is exothermic or endothermic, remember that endo goes with absorb and exo goes with release. We have to compare the two. We have to say, all right, well, was more energy absorbed than released, or was more energy released than absorbed? And we would know this if we were given the heat of the solution. So if they give you a written reaction and they give you the heat of solution, you can look at if it's positive or negative. If it's negative, that means that heat is being released. It's getting rid of that much energy in total. It has a net loss. okay? Where if it's positive, that means that overall I gained more in the beginning breaking the intermolecular forces than I did when forming new ones. So if you're given this number, you can just look at the sign. If you're actually doing the reaction or making the solution in class, then when you feel the test tube or whatever container you're doing this in, if something dissolving is releasing heat, that heat has to go somewhere and it's going to go out into the environment. It's going to go out into the surroundings. So if I'm holding this test tube, it's going to feel hot. And that's how I know it's exothermic. With endothermic, the solution is absorbing energy and it has to absorb that heat or that energy from somewhere, and it absorbs it from the surroundings. So me holding the test tube, which is part of the surroundings, this is going to feel cold in my hand. And we're going to actually get to do this in class as well, where we make two solutions, and I'll let you guys feel the difference between exo and endo. So that's pretty cool. So how do we know if something will dissolve in water? We know that ionic things dissolve in water. We just kind of spent the whole beginning of this video looking at NaCl. But we want to use the phrase like dissolves like, okay? Now, we looked at water before. We're going to look at it again. If I think about the symmetry of a water molecule, a water molecule is symmetrical if I cut it in half this way, but it's asymmetrical if I cut it in half this way. So when I have an asymmetrical molecule, that means that I have a polar molecule. Like dissolves like means that they have to have the same polarities to mix with each other. So ionic things are similar to polar things because they have a positive and a negative side, but polar things are very similar to other polar things. So if you put something ionic or polar in water, they will dissolve in each other. They will mix well because they're alike. They're both polar. So here's another example. This is an alcohol molecule. And if I look at its symmetry, it's asymmetrical. I have different things on this side than on this side. So if it's polar, you can guess that yes, it would dissolve in water. So sugar is an example of something that's polar. Alcohol molecules are polar. And salt, which is our ionic example. They will all dissolve in water because they're like water. Similarly, guys, if there's a substance and you don't know what the substance is, there's no way for you to look at its symmetry, right? If you put it in water, you can see what it does. If it dissolves, you can assume that substance is polar. If it doesn't, you can assume it's nonpolar. Okay, so that leads us down to here. If I look at this molecule here, I see that it is symmetrical in both directions, cutting it in half, which means it's a nonpolar molecule. So I know just from looking at it that this is not going to dissolve in water. So this happens to be an oil molecule. Anything that's symmetrical is not going to dissolve, right? Because they have different polarities. Okay. So this is a chart that you need to actually double check when we give you an ionic compound and ask you if it's soluble in water. In general, we say that ionic things, yes, are soluble, but there are some exceptions on this chart that you would have to be able to check out. Now, I did introduce this chart to you in another unit, so I'm going to kind of go over this quickly. But basically, we have these two main columns, a soluble column and an insoluble column. And soluble means that it dissolves in water, and insoluble means it doesn't dissolve. All right. So when I give you an ionic compound, and I know these are ionic because they have a metal and a nonmetal in them, I always want you to look for the second thing in the compound, like the nonmetal part of it, and I want you to find it in one of these two main columns first. So I'm going to say, all right, where can I find Cl? Cl is right here in the soluble column. Before I say that AgCl is soluble, I have to check to see that what it's bonded to is not in the exceptions. Ag happens to be in the exceptions. So chlorides are usually soluble unless they're bonded with Ag, Pb, or Hg. So if it's in the exceptions column, then it's the opposite of the main column. This would be an insoluble compound. This would not dissolve in water. That means instead of an AQ next to it, I would see an S. It stays solid. All right, let's look at the next one, NaOH. So I want to find OH in one of my main two columns. And I see it over here in the insoluble column. Before I say it's insoluble, I have to check the exceptions box. Do you see Na in the exceptions? I don't see Na physically written there, but I see group 1. Is Na in group 1 on the periodic table? Yes, it is. So typically, OH compounds are insoluble except for if they're bonded to something in group 1 or something else in this box. So this would be soluble. And the symbol we can write next to it would be an AQ. All right? I'm going to have you guys try the rest of these. Okay, so solutions. So far we've kind of talked about solutions forming from mixing something with water, which is a physical change. But solutions can also form from chemical reactions. So just as a review, I want you guys to look at these two reactions and write down which one's a physical change and which one's a chemical change. All right, hopefully you remembered that in a chemical reaction, we're creating new substances. So dissolving is physical, chemical is where we're creating different compounds and elements than we had before. In both cases, on the product side, there's something with an AQ next to it, right? So both of these scenarios make a solution. So what you guys are going to have to be able to do, not so much with dissolving, but when we're given a chemical reaction, you guys are going to have to be able to, when given reactants, predict the products, write the phase of those products, and then write a net ionic reaction, okay? So it sounds scary. Let's do this one together. When I have two compounds, I know that the only type of chemical reaction that can take place is a double replacement reaction, right? So my Na and my Ag are going to switch places. So Ag is going to combine with Cl. I have to look up their oxidation states. I have to crisscross them. The formula is AgCl. And I'm going to leave parentheses to look up the phase. The Na is going to combine with NO3. So I have to look up their oxidation states. Sorry, guys. This is so sensitive. -1. When I crisscross them, I get NaNO3. Okay, now if I go to table F, which is the table we were just looking at, I want to determine if those two things that I just made are soluble or insoluble in water. So if I go back up, I already looked at AgCl. I know that's insoluble. NaNO3, NO3 has no exceptions. So anytime something is bonded to Na3, I know it's soluble. So I want to write this is going to stay solid and this is going to be aqueous, right? Now I want to make sure I identified the products. Now I want to balance it. I have one Ag, one NO3, one Na, and one Cl on both sides. So this is actually balanced with ones in front of everything, so that's nice and easy. Identify solubility, I just did that. I said AgCl is insoluble and NaNO3 is aqueous. All right, now everything that's soluble, guys, is going to break up into ions. So dissociate means that wherever we see aqueous, we want to break this up into its ions. So guys, here are your oxidation states and your polyatomic ion charges coming back. That's aqueous, I broke it apart. NaCl is aqueous, I broke it apart. On the other side, AgCl is not aqueous, can't break it apart. NaNO3 is aqueous, breaking it apart. Okay? Now what you're going to do is you're going to compare the left to the right side of the arrow. Whatever is in common on both sides cancels out. So there's an NO3 here and an NO3 here. And there's an Na here and an Na here. Now you're going to rewrite what you're left with. Ag plus Cl minus. Those should both have aqueous next to them. They're going to make AgCl solid. And this is my net ionic equation for that reaction. Important, guys. If all aqueous, if there's nothing solid in my reaction, there's no net ionic equation. So no net ionic equation if all AQ, because then everything would break up into ions and both sides would cancel out. All right, so to end this video, guys, I would like you to try the next one. I want you to figure out what the products are, balance it, find their solubilities, and write a net ionic reaction, okay? And then this is what we will go over when we start class tomorrow.